Hey everyone, Amadou Jallo is here again, and today we're going to talk about crystalline structures in solid materials. You can see the weather today is beautiful again, and for the past 2 to 3 videos I've been doing it inside the classroom because the weather outside was not good enough, and I know it was really boring for some of you because I know the classroom is not a good place for most of you guys. Today I decided to bring again material science and engineering outside the classroom as always. So I will be exchanging. Sometimes I will do it inside the classroom when necessary, when we need some mathematics, and sometimes I will do it outside the classroom as well. So let's start. Crystalline solids in materials. So inside the classroom, we discussed already intensively about crystalline structures. So basically what I'm going to do now, I'm just going to repeat what I already talked about inside the classroom. Beautiful weather today, right? Look at this, so beautiful. So, and this is very important for us. This is very important, this beauty that we are seeing, this sun, because the sun is the source of the X-ray diffraction. So inside the classroom, what I talked about how we can determine the structures of materials, right? And we say that we can use an X-ray source to determine the structure, right? And somebody might want to ask, where does X-ray come from? Well, X-ray come from here. You see this sun? The X-ray come from the sun. Okay, there are other materials, radioactive materials that can give us X-ray, but most of all the X-rays come from the sun. So now we can generate X-rays inside the lab. However, what we talked the last time was that we have an X-ray source, and this source will penetrate. Okay, through X-ray can penetrate in almost every material. But however, X-ray cannot penetrate to lead. So it can stop lead. Lead can stop X-rays. So if we want to determine the crystal structure of, let's say, magnesium, okay, a pure magnesium, and when we say something is a pure, it have a single crystal, okay? So if we take a pure magnesium and place it in front of the X-ray, then we can able to determine the structure of this magnesium. How are we going to do that? Well, we can have an X-ray source. Well, not the one from the sun, obviously. We're going to use the one at the labs and to get an X-ray. Then we can have a lead plate that can block the X-ray. And this lead plate, we can make a small hole, tiny hole within the lead plate. And the reason why we make this tiny hole because we know that light travels in a straight line. So we want a particular light to go through the magnesium material so that we can able to determine its structure. Because if we allow all the rays that are coming from the X-ray to go through the magnesium, we can have crazy patterns. So that's why we make a tiny hole through the lead plate, and these incident beams will hit the magnesium, and this magnesium will diffract these beams, okay, these X-ray beams. So if we have a photographic plate, a Lowy photographic plate, it can determine, or it can detect rather, the patterns within the X-ray, within the magnesium material. And these patterns, we can look at these patterns, we can deduce the unit cell within this magnesium material. And the same thing we can use for different materials. We can use this for gold, we can use this for diamond, we can use this to determine the structure of different materials. And we can also use this to know whether this material is single crystal or polycrystalline. And what's the difference between single crystal and polycrystalline? Single crystal is when the material have only one unit that is repeating over the period of that material. Whereas polycrystalline, in the other hand, is when we have many, because poly mean many. Remember, we have polymers, many parts. Okay, poly mean many. So polycrystalline mean many crystallines, meaning that it have many, how can I say it, many units or many crystal structures within the material. So X-ray is a very good source. We know that obviously because the sun is always a good source of energy as well as light. We know about the electromagnetic spectrum. If you look at my first video, I make mention of that as well. So the next is that when we use the photographic Lawi photograph to detect these patterns, then we can determine the structure. And these patterns that are deflected, we can join these patterns. Every pattern within the material is a unit, is a plane being diffracted. Okay, so we can study these patterns, and we can able to use these patterns to determine the directions of a particular atom. We can use this to determine the planes. We can use this to determine the vectors of atoms within this material. So this is for crystalline materials. So when we do this in crystalline materials, we call this allotropy. Allotropy is the crystalline structure of metals. Okay, and now let's say we have other types of structures. Okay, we have non-crystalline materials. Non-crystalline materials is when these materials are not orderly arranged. Okay, they are randomly arranged along the material. That is what we call non-crystalline materials. However, for a unit cell, let me see, an example of a unit cell will be these blocks you see within this building. Let me see if I can get to those buildings and show you exactly what I'm talking about. All right, when we talk about unit cell, this is what we mean. You see this crystal structure here. This is a typical example of a unit cell. However, what we do is that we don't try to study the entire material, the entire building. What we do, we just identify this particular unit cell. We try to study the structure of this unit cell. What are the properties? And with this, we know that this is the same that is applied throughout this building that you are seeing behind me. So you can see that these are repetitive patterns. Okay, this is how the patterns are in the crystal structure of materials. Okay, solid material. This is how the patterns are there. So this is example of a unit cell. So this is a repetitive arrangement. So in a solid material, this is how atoms are arranged within the material. So however, what we do, we just consider this unit cell, and studying this unit cell will help us now to use that same method now for all the other materials, other unit cells. So now you saw a unit cell. So what we do with this unit cell? In this unit cell, we can able to determine the atoms, the position of atoms within the unit cell. We can also able to determine the direction. We can also able to determine how many atoms are within each unit cell. So we can able to determine also the density of atoms within this unit cell. So unit cell is a very important phenomenon. Like I said, I showed you already a typical example of a unit cell. So if we ask to compute the density, okay, of the unit cell, we can use this. If we ask to determine the direction of a unit cell, so for example, we can have 3 directions. We have the X, Y, and Z. However, if you go through that unit cell, you will not see an X, Y, and Z written there. So what are we going to do? We have to have a convention. We have to determine, okay, this is the X direction, this is the Y direction, and this is the Z direction. So that means a 3-dimensional space. So basically, this is how we do. But however, for non-crystalline materials, they are not arranged in this way. They are randomly arranged. Okay, so that's for crystalline solids in materials, and I hope you get the concept now of unit cell, direction, planes, okay, and crystalline and non-crystalline materials. So next we're going to talk about chapter 4, and until then, see you and have a great day.